Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the third lecture. In this lecture and in the next 5 lectures, we will be taking an overview of VLSI Design Flow, and then in the rest of the lectures of this course, we will be looking at various design tasks in more detail. We have taken this approach of first taking an overview of VLSI Design Flow, so that later on when we look into the various design tasks in more detail, we will be able to appreciate the linkages between one design task and the other. We can also understand the impact of one design task on the other and how we can optimize a given design task such that down the flow other task gets benefit out of it. So by taking this or taking an overview and then going into the detail of each of the tasks helps us to gain the understanding of the entire design flow in detail. So in this lecture, we will be covering the topics. First of all, an overview of how the design flow is structured, and then we will be looking at an important concept which is known as abstraction. And then we will be looking into pre-RTL methodologies and hardware software partitioning. Let us first look into the top level problem that we are trying to solve in VLSI design flow. The top level problem is that we have got some idea of implementing a system, and that system is doing some useful work. For example, it is doing some processing, or it is doing some computation, or it may be say controlling a robot or doing some useful work for us. So that is the starting point of chip design, or that is the idea we are having. And at the end of the flow, what we want is a chip which is delivering that task, and that chip should be manufactured in bulk, and the manufacture and the fabrication of chip should be such that that the whole process is a profitable for the person who is undertaking this venture. Now this is a complicated task. It can be accomplished in many ways. Some of them can lead to profitable chip design, and some may not, right? And some can actually fail. So to tackle this complicated problem, what strategy do we follow? We follow the strategy of divide and conquer. So what we do is that we break the entire chip designing task and chip manufacturing task into multiple steps and carry out those steps sequentially. So let us look into at a broad level, what are those tasks? So given an idea and its implementation to a chip, within this flow, there are a design undergoes through a lot of transformations. Nevertheless, we can identify a few milestones through which a design goes through. And what are those milestones? The first one, we can say that it is the RTL. RTL is a design representation in a register transfer level. It is typically written in Verilog or VHDL language, and then we take this RTL and it goes through the design process, and finally we get a layout which we say that it is in the form of graphical database system, and that is representing a layout. So from the idea to the chip, we have identified two important milestones. One is the RTL and the GDS, and based on these milestones we can divide the entire process flow into three parts. The first part is from idea to the RTL. So in this step, what we do is that we take a high level idea concept of a product and represent the hardware portion of the idea into an RTL. So that we can call it as idea to RTL flow, or we also call it as system level design. And then once we have an RTL, then comes the RTL to GDS flow. So in this, what we do is that we take an RTL and take it through various stages of logical and physical design. What does logical and physical design mean? We'll look into that in the later part of this course. And at the end of the RTL to GDS flow, we get a layout which is represented in GDS form. And once we have got the layout, then it goes to the foundry for fabrication, and that we can say is the GDS to chip processes. It takes a GDS, prepares mask for a given GDS and fabricates, tests, packages chips, and then it goes to the market. So, in this today's lecture, we will be looking primarily at this part, right? And in later lectures, we will be taking an overview of this RTL to GDS flow, and then we will be also going into GDS to chip processes flow. We will be taking an overview, or we will be looking into them very briefly. But the later part, or the main part of this course, is this RTL to GDS flow, where a lot of effort is needed, not only in implementation of the design, but also in verification of the design. We have taken a top level view of what VLSI design flow is and how an idea is converted to a chip. Now, let us look into an important concept which is known as abstraction and how it relates to VLSI design flow. So, what is abstraction? Abstraction is basically hiding lower level details in a description. So, as the design moves through VLSI design flow, details go on adding in the design, and as a result abstraction decreases. Why abstraction decreases? Because abstraction means hiding lower level details and keeping only the thing which is required at the top level, right? So, as design moves through the VLSI design flow, more details are added and abstraction decreases. So, if we look into the three parts of the design flow that we just discussed, in the from idea to RTL flow, the abstraction is very high, right? And we are representing a design in terms of system and behavior. Later on, when it goes to RTL to GDS flow, as the design moves through various stages of RTL to GDS flow, the abstraction goes on decreasing, and the design gets transformed from first to RTL, to logic gates, then transistor, and finally to the layout. And once we have got the layout, then there is no abstraction. All the details required for fabrication are already there, and then the actual implementation starts, and the design in the fabrication step is represented by mask and integrated circuits, or the final integrated circuit. Now, why do we do abstraction, or why do we abstract out information in VLSI design flow especially at the earlier stages of design? So, to understand that, we should first see that for a design task, what are important considerations are. There are two important considerations. The first one is optimization. Optimization means choosing right combination of design parameters to obtain desired QR by trading off some other QR measures, right? So, the optimization is basically trying to find suitable parameters for the design, so that we get a better quality of result or figures of merit, right? That is one part of a design task. Another part of the design task is the turnaround time. Now, what is turnaround time? Turnaround time is the time taken to make changes in a design. Ideally, we want to make these changes as quickly as possible, right? Why do we want to do that? Because we want to design or make design of a chip as soon as possible, so that the chip can be then fabricated, and then it goes out to the market, and it succeeds in the competition in the market. So, the sooner we bring a product, the more likely it will succeed, and therefore turnaround time is very important, especially in the semiconductor industry. Now, when we do abstraction, what benefits do we get? When we do abstraction at the higher level, the details in the design are less. Okay, so at the higher level, abstraction is large, is more, and therefore large number of solutions can be analyzed in less amount of time, right? So when we remove details of a design, then what happens is that only some part of the design which are actually important, maybe the functionality and other things, those are important, and only a few implementation details are available at the top level. So when we keep only a few details of a design, then it allows us to explore the design space more easily in terms of runtime by the tools, and also the human designer effort. Why? Because when the details are less, then a human designer can look into more details, because when there are less entities, then a designer can focus on those less number of entities and can optimize it manually, or can give hints to the tool and get a better QR. And so as the result of optimization at higher level of abstraction is expected to be better. Okay, so if the scope of optimization is very high at the top level, right? Because there we can look into there are less details, so we can try out many options and then choose the best out of it. And therefore the scope of optimization is very high at in the system level design, or at the idea to the RTL flow, the first part of the flow that we discussed. And the turnaround time will be also be low, because the details are less, so we need to add or change a fewer details in the design, and therefore turnaround time can be quicker. And in the RTL to GDS flow, what happens is that as the design flow moves, the more details are added, and therefore making changes become difficult, and the scope of optimization decreases, because we can try out less number of options, right? And when we go into the last part, that is the fabrication, there is no optimization. Only if some corrections are required, those are made, and those are very costly. Now, to give you an illustration that what are various levels of abstraction, let's take an example. Now consider that the functionality is represented in two ways. First, in terms of logic formula. This is one level of abstraction in which we are representing a function in terms of logic formula. For example, f is equal to a plus b whole part, right? Now the same function can be represented in a layout also in terms of standard cells and a NOR gate, or a standard cell which is delivering a NOR function, and we are making a layout and placing it and also making a connection out of it, right? So these are two different levels of abstraction, right? Now let us understand that which of the above representation has greater abstraction. Since in the logic formula there is less detail, it is only defining the functionality, right? And the details about how it is implemented in terms of layout and other things is missing. The level of abstraction is higher in for the first representation, right? So in the first representation the abstraction is more, and the smaller turnaround time will be required in the first representation. Why? Because if we want to make a change in the implementation, suppose we want to represent f is equal to a plus b whole bar as a bar dot b bar, right? So this kind of transformation can be done very easily at the logic formula level. But what if we want to do a similar kind of transformation in the layout? Then we might need to change the NOR gate to say an AND gate, and then we need to have an inverter and so on, and then we need to place these gates and also make the connections on the layout, right? So that's the turnaround time that will be required in making change in the layout representation or the B representation will be much higher than in the A representation. Okay, so the question comes that where the accuracy in evaluation of different option will be more. So we understand that in the logic formula the details are missing, meaning that we don't know the details of that how the NOR gate is implemented. So we cannot compute the delay, area and other things, right. However, if the layout is there, then we can estimate the area, estimate the delay and other figures of merit much more accurately. So greater accuracy in evaluation will be in the B representation, right. So what we see is that as the design moves from a higher abstraction level to the lower abstraction level, the details are added, and as such when details are added, then the scope of optimization reduces, but the estimate of the figures of merit, those become more accurate. Now let us look at pre-RTL methodologies. Pre-RTL methodologies are the design tasks that we undertake before getting an RTL. In this part of the VLSI design flow, we decide the various components that will be required for a system. These components may be hardware, these components may be software, and also we decide that how these components interact with each other. Therefore, these designs or this design step or pre-RTL methodologies is also known as the system level design. In this, when we have an idea and we want to get a product out of it, so what we do is that initially whenever there is an idea, the first thing is that we evaluate whether that idea is worthwhile or not. So we check for the market requirement, we look for we analyze financial viability, and we also look into the technical feasibility. If all these things are positive, then we move to the next step, that is creating a specification for the product, right. So when we define a specification, we will decide on the features that we need for the product and the PPA or the figures of merit that are relevant for the product. For example, at what clock frequency it should work, or what will the power dissipation that will be allowed for the chip, and the cost and other kind of figures of merit. And then we also decide what should be the schedule of making this product and what is known as time to market, right. So the time to market is that how much time it takes for an idea to get its implemented and the product coming out to the market. Ideally, we want to keep it as small as possible. And once we have got the specification and the features that needs to be implemented for a product, then the step comes what is known as hardware software partitioning. So in this hardware software partitioning step, we identify various components that will be required for the system. So these at the broad level, these components can be either hardware or it can be software, right. Now we need to decide that which component needs to be implemented in software and which component needs to be implemented in hardware, and this step is known as hardware software partitioning. Once we have decided that this part what will be the hardware portion of the specification that needs to be implemented, then it goes through IC design and manufacture phase, in which we build the hardware, right. And in the similar manner, the software portion of the specification goes through the software development process, and the executables and the firmware, device drivers, apps, etc., those are final result of the software development. Once both hardware and software both are available, and there will be some components which are already existing, which we can directly reuse at the system level. When all of them are ready, then we do a system level integration. We combine all these components together, we do some validation, we do testing, and at the end of this, the product comes out of it, right. So this is a very top level view of top level view of system level design, right. So now what we will do is that we will be looking into a few of these steps or this system level design steps in more detail. So it is worthy to point out that the system level design varies depending on the type of products we are designing or the type of functionality we are implementing. For example, whether it is a processor or a signal processing chip or maybe a other kind of controller or other kind of design, or the exact step that is or design task that will be undertaken under in system level design will be varying. However, let us look at a few design tasks which are common to all the system level design or which are widely used. Okay. So let us look into the first part, that is hardware software partitioning, and this is one of the integral part of system level design. So what is hardware software partitioning and why do we want to do it? So the motivation for doing hardware software partitioning is that we want to exploit the merits of both hardware and software. So now hardware has got some merit, it has also got some demerit, now and software has got some merit and also demerit, right. Now when we combine hardware and software and get a system out of it, what we want is that the good thing of hardware is extract or is utilized in the system and good thing of software is also utilized, and as a result we get a product of an excellent quality, right. So the what are the good things of hardware and what are good things of software? Let us understand that first. The good thing about hardware is that it can deliver a very high performance, meaning that it can be very it can deliver a very high speed. Why it can give you a very high speed is that hardware can be made such that there are parallel circuits, right, and all of them can work concurrently, and as such a given task can be completed much more quickly. While if we look into the software, that software if it is running on a processor, and assuming that the processor is only is running in a sequential manner, taking one instruction and doing the processing and giving you the result, there will be a kind of sequential operation in for the software, but for hardware lot of parallelization can be done, and therefore that is the biggest merit of hardware, is that it can deliver a very high performance. Now what are good things about the about the software? The good thing about software is that the development of the software is much more easy. Why? Because it is less complicated than making a hardware or designing the hardware. And also the risk involved in software is much lesser. Why? Because if we find any error in a software, we can simply debug it and then and make the change in the code, recompile it, and we are done. But if there is a problem in the hardware, we may need to respin it, right? We need to make the we need to redesign the hardware. We may require to redesign the hardware. We may need to change the mask and other things, and therefore it may be costly and also time taking, right? And the other good thing about software is that a lot of customization can be done, right? You can make that code, make a code which can do many things based on the requirement, and it is easy to customize in the case of software. But for hardware, you need hardware hooks and other things which are more difficult to implement. And for the development time of the software is much lesser compared to the hardware, because hardware design is a more complex task, as we'll be seeing in this course in the subsequent lectures. Now to understand how do we do hardware software partitioning, let's understand or take a look at a typical system in which both hardware and software coexist, right? So this figure shows such a kind of system, right? In this, what we have is a general purpose microprocessor, okay, over which the software part is running, right. So, one instruction is running, the processor is giving the result, and then it is utilized again and so on. So, the software is running sequentially on a general purpose microprocessor, and then there is a dedicated hardware, right, which performs some task, and this is the hardware we are talking about that we can implement in a system. This hardware, this is also known as hardware accelerator, which can give the result very fast. It is in this figure what we are showing is only one dedicated hardware. There can be multiple dedicated hardwares, right, and all of them can be maybe working in parallel, and as a result of that the whole system will be giving the result very fast. Okay, there can be memory, and all these things can be interacting through or sharing information through some bus, right. So, here a simple bus is shown, but there in a chip or in a system realized on a chip, these things can be the connections can be very complicated also, right. This is so the figure that I have shown here is just for the illustrative purpose. I have just shown you a kind of system where hardware and software both are working together. So, the hardware usually runs as parallel circuits and can have very good PPA, and that is why these are known as hardware accelerators, and it can be implemented in full custom IC, ASIC or FPG, right. This dedicated hardware can be implemented in various kinds of design styles, and then the software usually runs sequentially on the general purpose processor, right. Now, the hardware software partitioning step, what it does is that it tries to map a functionality which should go into this software part running on a general purpose microprocessor, and the functionality which should go into this hardware part or multiple such hardwares or different kinds of hardware which will be hooked onto the system. Now, let us look into an example of how partitioning can be done, right. Just a simple example, let us consider an video compression algorithm, right. So, now in this algorithm we can divide it into two parts. The first part is the one which is computing discrete cosine transform. So, assume that for the time being that this computation is done many times, and this is the bottleneck for the algorithm. It is taking lot of time, the computation of discrete cosine transform. And then there are other computation, for example, frame handling and other computation which are also being done. But the point is that here we are assuming for the time being that the part of the algorithm which is bottleneck meaning that a lot of runtime, say out of 100% runtime, 80% is going in computing DCT, right. Now, in this case, how do we do a hardware software partitioning? What we can do is that the DCT part can be computed separately on a hardware on a hardware or a hardware accelerator, and it can be computed using parallel circuits. That circuit can be optimized so that the performance can be, say, 1000 times faster than a software doing a similar kind of computation on general purpose computer or processor, right. And it can be several orders of magnitude faster and more energy efficient. We can optimize other QR measures also, for example, energy efficiency or power dissipation required for the computation of DCT and other things. Those things can also be optimized in the hardware that we design. And the other part, that is frame handling and other computation, those can be actually delegated to the software part, and that software will be running on a general purpose processor in the same system, right. So, software running on the general purpose microprocessor, what it will give the benefit is that it will provide lot of flexibility. For example, later on if frame handling algorithm and other things needs to be changed, those can be changed just by the software modifications. No change in hardware will be required, right. So, this is just an example that given an algorithm, how can we partition into hardware part and the software part. We typically choose the part which is very critical and which is basically bottleneck at a system level to implement in hardware, and the part where we require a lot of flexibility in the algorithm or where the change can be there, those we can implement in the software. Now, hardware software partitioning can be done in many ways, right? So, it can be done in many ways. For the illustrative purpose, let us look into one way in which hardware software partitioning can be done, just to illustrate that what are the challenges and what decisions needs to be made during hardware software partitioning step. So, let us assume that the objective of hardware software partitioning is to find a minimum set of functions that need to be implemented in hardware to achieve the desired performance, right. So, what we say that initially a algorithm is given to us and that algorithm is implemented entirely in software, right. Now, out of that, all the functions which are implemented in software, we want to partition it or move a subset of that function or that set of functions to hardware, right. And what that subset should be, that we need to find out. So, in this figure I am showing you a flow chart for how hardware software partitioning can be done. Initially, so we are representing here two sets, one is S and the other is H. So, the set S contains all the functions which are implemented in software and H contains all the functions which are implemented in hardware. So, initially all the functions of the algorithm are in S, right, and H is an empty set, right. H is an empty set and everything is implemented in software, right. And then what we say is that we are also given an acceptable performance P, right, that the performance should be better than P, it should not be worse than P, right. So, by hardware software partitioning, what we want to attain is that the performance should come be above a given threshold P, right. And then there are parameters of the algorithm N, which decides the maximum number of functions to be moved to hardware in each iteration. What is the use of N? We will see later, right. So, this is the input. Input is the set of functions which needs to be implemented in for a given algorithm, and all are initially in the software, right. And at the end, what we want the output from this software hardware partitioning is a set of function H, right, a set of function H that needs to be implemented in hardware, right. Initially H is empty, but as this algorithm will progress, the H will be populated or that set will get filled, and it will be filled with minimal set of functions such that the performance becomes above the given threshold. Okay. Now, let us see how to achieve this in hardware software partition. So, when we do hardware software partitioning, we need to measure that what is the performance, right. So, in this pseudo code or in this flow chart, I am showing the task of measuring the performance using the function evaluate H comma S, right. So, when we are given an whenever this algorithm enters, the first thing is that it measures the speed, what is the current speed or what is the current performance of the partition, that is in the initial stage H is empty while S contains all the functions of the given algorithm. Now, if the speed is already acceptable, right, if it is already greater than P, right, if speed is greater than P, then we need not do any partitioning, right. In that case, everything can be implemented in the software part, it goes through this, right, everything is, so got the required partition, nothing to do, right. If it is not, if the performance is not as per or it is below the threshold P, then what we do is a step which is known as profile HS. What is this step doing is that it is measuring the frequency or duration of each function calls, right? If we have all the functions of the algorithm implemented in software, right? Now what we do is that for each of the function we do a step known as profiling. In profiling is basically running the given test cases using a profiler. Profiler is a tool that measures that how much runtime is taken by each function in a given executable, right? So initially everything is in software. We do a profiling of the code to find out that which functions out of that is taking more time. For example, there are say 4 functions f1, f2, f3, f4, right? So the profile will give an information that f1 is taking say 10% of the time, f2 is taking say 70% of the time, f3 is taking say 10% of time, and f4 is also taking 10% of time, right? This is what an information will be given by the profiler, right? Now using the profiler information we can identify which is the bottleneck function. So clearly in this case f2 is the bottleneck function, right? So in each iteration what we do is that we identify ith most severe bottleneck function fi, right? So in this case the first bottleneck function is f2, right? So once we identify the ith most severe bottleneck function, what we do is that we assume that fi is implemented in hardware, right? We assume that. So now in h we'll get an element, we'll add an element which is f2, right? So f2 will be added to the set h, right? That is what it is doing. H is equal to h union fi, that is we are adding an element f2 to h, and what we are doing simultaneously, s is equal to s minus s fi, meaning that we are removing f2 from the set of function in s, right? So it is kind of indicating that this function f2 has moved to hardware rather than software, right? Once we do that, then what we do is that we evaluate the new speed, right? Ideally we want this the new speed should be better than the earlier speed. Why? Because hardware can probably do things faster, right, compared to software, and therefore the new speed will be greater than the earlier, right? Now if this performance is improving to such an extent that it crosses the threshold, right, if the threshold was p, then we got the required partition. If not, the next function will be taken, right? In this case f1, f3, f4 all are having equal percentage. So in the next one maybe say f1 will be picked, any one will be picked out of them, right? The first appearing function in the when the percentage match will be taken, right? Now we move f1 also into h and then measure, right? Now if the speed is acceptable, we are done. If not, then we continue moving a function from software side to the hardware side, right? So we measure the performance and check whether target performance p is met. So it moves maximum of n most critical bottleneck functions to the hardware, right? So it goes on doing it n times, right? Now what happens is that in doing this n times, either we get the partition get the required partition, or the performance of the system improves to such an extent that it crosses the threshold p, or it may not deliver the sufficient gain, and then we need to iterate it, right? Now when this iteration will terminate, it will be terminating when we are able to achieve the target p, right? That is one criteria, then this algorithm will terminate. Other terminating criteria is that no improvement even after moving n functions to the hardware. Even if we have moved n times, right? Even if we have moved n times, even when we have moved n functions from software to hardware, we are not getting an improvement, right? When we are not getting an improvement, we say that no partition can be formed, right? Why can we not get an improvement? Even when we have moved a function from software to hardware, there can be many reasons. One of the primary reason can be the communication. See, when we when we implement everything in software, everything is going from software to software and so on, right? But when there is a partitioning between software and hardware, then there will be a time taken in the communication between software and hardware also, right? And there will be also be dependency among the data, and it may be that hardware is waiting for the data and therefore it cannot produce the result even though it is ready, right? And therefore because of the data dependency, there can be less gain, or even if the gain that we get by the implementing in hardware, that can be offset by the extra time taken in communication, right? And therefore even if we move some function out of from software to the hardware, we may not get an expected gain, and in that case we cannot find a suitable partition. So this is a very simplistic method of hardware software partitioning. This is just for the illustrative purpose. It takes a greedy approach and to settle to some minima, right? To or getting to a case in which we are able to meet the performance and incur the cost of hardware the minimum, right? We are assuming here that the hardware is costly, therefore we don't want to move everything to the hardware. We want to move minimum set of functions from the software to hardware. That was what we started our this algorithm is assuming, right? Now, what are challenges in this kind of implementation or hardware software partitioning in general? The first challenge is the performance estimation. What is this challenge is that when we say that we move the function f from software to hardware, and then we evaluate the performance to see whether it is below the threshold or not. Now the problem is that we don't have the hardware yet, as yet, right? We have just assumed that that software function has moved to hardware, but the hardware is still non-existent. The hardware has to be made, it has to be designed, it has to be fabricated. Then only we can actually get a fair idea or get the exact numbers that by how much it is performance is improved, right? So the non-existence of hardware will be the primary concern in hardware software partitioning. Now how do we try to tackle this problem? We tackle this problem by implementing the hardware either in say FPGA, which can be designed very quickly because hardware is already there, we need to program it, and therefore we assume that the things has moved to FPGA, and based on that we can make some estimate that if that hardware that function is moved from software to hardware, how much gain do we expect, right? Even for ASIC we can extrapolate that number to something and then check that whether if we implement that function in ASIC, whether we will get a sufficient gain or not. The second approach can be taken is that we can say that the given function f1 is implemented in hardware, but we take through a quick design flow. For example, we do a kind of behavior synthesis or high level synthesis, implement it, do a placement routing and other things at a very crude level and estimate or get a number out of it, right? That can be another way to deal with this problem. Then the second challenge is regarding the verification of hardware and software. Now earlier everything was implemented in software. Now we are saying something is implemented in hardware, something in software. Now we also need to ensure that once these two combine together, they still give the required functionality. And we need to do that kind of verification. And that kind of verification is a difficult thing because the hardware is still non-existent. So various approaches are taken to deal with this problem. For example, what is known as co-simulation, hardware software co-simulation, in which we assume some model of the hardware or timing model for the hardware, and using that timing model of the hardware and the existing software, we try to simulate it and get a fair idea of whether the system will work even when these two things are implemented together or combined together. So this is the reference to which you can refer to for more information on this topic. And this brings us to the end of this lecture. In this lecture, we have looked into an important concept of abstraction, And then we looked into the idea to RTL flow or the system level design flow. In particular, we looked into hardware software partitioning. In the next lecture, we will be looking into another aspect of system level design, that is behavior level synthesis. Thank you very much.